Hello everybody. In this video we are going to discuss binomial and geometric distributions. By the end you will be able to identify scenarios in which you can differentiate between binomial and geometric settings, then calculate probabilities for each. This is awesome because you are going to learn how to calculate probabilities of really complex scenarios in an actually very simple fashion. Let's start off by addressing our essential question, which is how do you determine which formula to use for a probability question? Well, to answer this, we first need to know what kind of probability scenario we are in. And that leads us to one of my favorite topics of probability, binomial settings. Let's consider this example. Someone invites you to play a game in which you roll a die 10 times. If you roll exactly 2 sixes in those 10 rolls, you win. Well, naturally we would want to know what is your probability of winning this game. This scenario is an example of what we call a binomial setting, one in which several independent trials of the same chance process are carried out, and each outcome can be defined as either success or failure. Well, how do we know this is indeed a binomial setting? We break down the definition using this handy acronym. Check your bins. The first thing to check is if the outcomes are indeed binary. Can each outcome be classified as either a success or as a failure? Well, in this case, we say yes, because a success is obviously going to be a 6, and a failure is anything else. It's a not 6. Next, we need to make sure we have independent trials. Now, we understand that knowing what we got on one roll of die doesn't help us predict the next roll. So we're all good here because each roll of the die is independent of the next. Next, we need to make sure we have a fixed number of trials, n. Now in this case, we know we are rolling 10 times. We aren't just rolling indefinitely, we have decided to roll exactly 10. No more, no less. Check. Finally, we need to make sure that we have the same probability of success p for each trial. Well, let's go ahead and assume that this is not a trick die. We know that a 6 has a 1 in 6 chance of landing on each roll. So in this case, we are all set. At this point, if you need to pause to catch up filling in blanks, please go ahead and do so and hit play to resume. Now that we know we have a binomial setting, how do we calculate the probability of getting exactly 2 sixes in 10 rolls? Well, there are 3 steps. We want to account for successes, account for your failures, and determine how many ways you can get the outcome you are looking for. Let's first talk about the successes. We want exactly 2 sixes, and each one has a 1 in 6 chance of showing up on the die. Now let's say, for example, we get our 2 sixes on the first 2 rolls. That means 6 and 6, each with a 1 in 6 chance. Since these are independent rules, we can use a special multiplication rule, which makes it 1 6 times 1 6, or more simply, 1 over 6 to the second power. Now for our failures. We know the probability of getting a not 6 is every other outcome, or 5 out of 6. And we know that we want exactly 8 failures. Well, again, these are all independent, so that means we have 8 5/6 that we need to multiply, or 5 out of 6 to the 8th power. The last step is to account for how many ways we can see this. I suggested that we got our 2 sixes immediately, then got no more 6s in the rest of those 10 rolls. But obviously we can get the 6s at the end, we could get them somewhere in the middle, or they could be the first and the very last. Those could be the 6s. Meaning there could be potentially dozens or hundreds of different combinations of getting exactly 2 sixes. That means we need to calculate the combination, choosing from 10 rolls to get exactly 2 successes. This gives us what is known as the binomial coefficient, this 10 choose 2 value, which accounts for all combinations of ways that your successes can occur. Now, this formula should bring you back to combinations and permutations from geometry class using factorials, and I know that gets you very excited. But the even better news is we're going to use our calculator to give us this value. So we don't need to stress out about this formula at all. What is important for you is to know that this is a combinations calculation, where n represents the number of trials, k represents the number of successes, and you read it as from n choose k. Now, you can find this in your calculator, possibly listed as either NCK or NCR. So let's actually switch over to a calculator now and see what this is going to look like. In our calculators, you'll find this by accessing your menu, then probability, number 5, then we go to combinations, number 3, and it comes up as NCR. What you need to do is enter in your total number of trials, 10, and your number of successes, 2, separated by a comma. Press enter and you will see that there are exactly 45 total ways to make this happen. Now obviously this was not intuitive, so we needed this shortcut of binomial coefficient to see all of the different ways we could get exactly 2 successes in 10 trials. Now, to put it all together, we just need to multiply all of those quantities we found first. But let's break down the formula, where we can see that n choose k is telling us how many ways that we can get a certain number of successes in a certain number of trials. P to the k represents our probability of success and the number of successes. And 1 minus p to the n minus k represents our probability of failure and all of our failures. So, let's write out our example. P of x equaling 2 to represent getting exactly 2 6s in our 10 rolls. 10 choose k to tell us how many different ways we can get those 2 successes. Probability of success is 1/6, and we want 2 successes, so that's 1/6 to the 2nd power. And then our probability of failure, 5/6, and we want 8 total failures, so that's 5/6 to the 8th power. And that does it. Pretty simple to set up. Plug it all into your calculator to see what is the probability of winning, and we see we have about a 29% chance of success. So to summarize our strategies, once you've identified binomial settings by checking your bins, you want to identify your number of trials, n, your probability of success, p, and your number of successes, k. Use that to build out the formula by accounting for all of your successes, your failures, and how many ways it can happen, and you'll be able to tackle any binomial probability question easy peasy. Don't like formulas? Well, guess what? We've got you covered there too. So long as you have a good graphing calculator. The calculator command binom PDF can be used to find exactly a certain number of successes. Let's take a look what that looks like in the calculator. This can be found by going into our menu and then choosing number 5 for probability, then this time distributions. And toward the bottom we are going to see binom PDF. That's option A. So if we type in A, we get our command enter in your number of trials. In this case it was 10. Our probability of success, it was 1/6. You can just write in the fraction, and then our x value is going to be like k, our total number of successes. Just like we practice, write out your n, your p, and your k. Enter it in, and you can see your binom PDF is going to give you the exact same value that we found when we did it by hand. Easy enough. Alright, well now what happens if we change the game? And in order to win, you have to get at least 5 6s in 10 rolls. Well, we could use the binomial formula several times to include getting 5 6s, or getting 6 6s, or getting 7 6s, and adding up all of these probabilities until we finally get to that last one, the 10th roll, all 10 rolls being 6s. As any one of these would represent the outcome of you winning, you have to add up all of those probabilities. Well, that's really time consuming. Well, just like we had a norm CDF calculator, guess what we've got? A binom CDF calculator as well. We use this for any inequality with binomial settings. You just need to be careful about the lower and upper bounds. Let's go back to the calculator and see how that's going to work. Again, we're going to go into our menu, then we choose probability and distributions one more time, but this time we're going to go all the way down past binom PDF, and you should see option B is binom CDF. Here, again, our number of trials, it's still 10. Our probability of success is still 1 out of 6, but now we have lower bounds and upper bounds that we need to account for. Well, we said you have to get at least 5 6s in order to win. So that means the fewest number of 6s we'd want to see is 5. That's our lower bound. Now we can get up to a total of 10 6s because that's the total number of times we're rolling the die. So our upper bound is 10. Go in and enter, and you get your result. Surprisingly, we get a pretty small probability of only about 1.5%. Why is that? we're including more outcomes, right? So we should see a larger probability. Well, this just goes to show how actually difficult or unlikely it is to get several sixes or several of the same outcomes. So that's pretty easy. To get full credit, you just need to show your work by writing out the binom CDF command, just the same way you saw it in your calculator along with your result. But you also do need to make sure you label your n, your p, your lower bound, and upper bound when writing out your response. So that's pretty simple to do. Now, to differentiate between when to use the PDF or the CDF function in your calculator, you just need to be on the lookout for key words. Anything that references exactly or a specific certain number of successes, that's a binom PDF situation. Whereas any kind of inequality phrase like less than, more than, at most, or no more than, those are going to represent multiple outcomes for binom CDF. Now, because this formula describes all outcomes of a binomial setting, that means the entire distribution is indeed predictable, meaning we can easily calculate the mean and standard deviation in a binomial setting. The formula for mean of a binomial is n times p, and the standard deviation is the square root of n times p times the quantity 1 minus p. Applying that to our scenario here, rolling 10 times with a probability of success 1 out of 6, we can see that we have a mean of about 10 out of 6, or 1.66667 sixes in 10 rolls on average. That seems weird, but remember, this is an average after playing this game in which you roll 10 times per game, and you're playing this game many, many times. So getting an average that seems like it's impossible is actually totally okay. We just simply interpret that mean as the average number of successes in a certain number of trials. In this case, that means we are going to have an average of 1.6667 rolls or sixes rolled in every 10 rolls of the die. For standard deviation, plugging in for n, p, and 1 minus p, we have 10 times 1 over 6 times 5 over 6, take the square root of everything, which gives us 1.1785. Meaning the number of sixes rolled in 10 tries will typically vary from the mean by 1.1785 sixes. Finally, we are going to discuss what is known as the geometric distribution. The geometric distribution is a special case of the binomial distribution in which we perform several independent binary trials until the first success is obtained. The number of trials in which the first success obtained is recorded along with the probability in the complete distribution. And what we are actually asking or answering is the probability of your first success happening on that kth trial is provided in the geometric distribution. So let's consider that we don't get our first 6 until the 8th roll. Well, that's a geometric setting because we are looking at our first success coming on a specified roll. That means we rolled 7 consecutive times not getting a 6. But then finally on our 8th trial, we did. Thus, the probability can be calculated as such. Accounting for all of the failures we had first, that's 5 out of 6 raised up to the 7th power, then finally our success, 1 out of 6, giving us a probability of about 4.65%. And that's it. Super simple. There's no need for the binomial coefficient here, as there's no other way that this can occur. There must be 7 straight failures for this scenario to occur. And our last one must be success. We don't raise 1/6 to any power because in this setting, we're stopping as soon as we get our success. Thus, in general, we can calculate our probability of first success by accounting for our failures in 1 minus p to the k minus 1 power, then finally our first success in multiplying by p, and that's it. Now naturally, geometric probabilities have their own geom PDF and geom CDF commands as well, where geom CDF is going to calculate the probability that your first success comes between 2 specified trials. These often can be combined with complement rules to creatively calculate complex probabilities that we will examine later in class. The final aspect to examine with geometric probabilities is calculating its mean, just like we did with the binomial distribution. The average number of trials needed for our first success is the question that we can potentially answer. So, in this setting, on average, how many rolls will it take until we get a 6? How many times should we expect to have to roll before we get that 6? Well, the formula for the mean is slightly different than the binomial mean, but just as easy. The mean for a geometric distribution is 1 divided by p. So in our case, 1 over p is 1 over 6. Looks gross, but dividing by fractions is the same as multiplying by the reciprocal of the denominator. Hence, we have 1 times 6 over 1, which that's really easy. We get 6. Very serendipitous that it was that simple, or maybe not if you're just really tired of seeing all of these 6s. We can interpret this as it being it's going to take 6 rolls on average to get our first 6. Either way, these formulas are available for you to find on your AP Stats formula sheet, so you just need to know how to apply them and to be able to determine whether we're in a binomial or a geometric setting. Guess what? That's it. We're all done. Using these ideas, you can identify when you have a binomial or geometric setting, calculate binomial and geometric probabilities, and also determine the mean for each one of those settings too. Thank you guys for watching. Have a great day. I'll see you next time.